Okay, finishing up section 9.2, let's go ahead and look at one more example of a hypothesis test. Example, in 2007, according to the National Institute on Drug Abuse, 31.72% of 12th graders had abused marijuana the prior year. Since then, efforts such as anti-drug education programs have been implemented to deter drug use. A current sample of 218 12th graders indicated that 64 of them abused marijuana in the last year. Part A. Perform a hypothesis test at the 5% significance level to determine if the true percentage of the current 12th graders that abused marijuana during the last year has decreased from the 2007 level. Okay, so very clearly it's telling us that it's a hypothesis test. So in a hypothesis test, step 1 is to set up the null and alternative hypotheses, H0 and H1. And the first step of that process is to determine if this is a test about a mean or a proportion. And it says we're trying to determine if the true percentage, so if we're trying to test the true percentage, that would not be mu, that would be p. So HO is going to have p equal to some value. And then the next job on our part is to figure out what that value should be. And it says that we're trying to see if the true percentage of current 12th graders that abused marijuana during the last year has decreased from the 2007 level. So when it says decreased, that is a directional statement, so that goes in H1, and decrease would be a less than. And it's decreased from the 2007 level is what we're trying to show, so we'd want to put the 2007 level right here. And at the beginning of the problem it says in 2007 it was 31.72%. So I'm going to put that here, and then that would also always be what we put in H0. These two always have the same number. So we're going to put that down for P, but we do have to remember that when you put a percentage in to your null and alternative and in any of the math of the process, you're going to change that to a decimal. So for HO, I'm going to put as a default that maybe P currently is the same as it used to be, 3172, and then my alternative that I'm really trying to show is that no, it's decreased since then, and that now it's less than 0.3172. So that's step 1, and then step 2 would be to set our significance level, and that's always an easy step. We just need to find that in the problem, and right here they say they want us to do this one at the standard 5% significance level. So I'm going to write down that alpha equals 0.05, and then I'll go ahead and fence that off. Just a reminder, that is the setup phase, and this is the part that in a real hypothesis test would always get done before any data was collected. So when we're doing one of these as a book problem, we're always going to get all the information at once, but when you're doing a hypothesis test, you're not supposed to have your data influencing how you set up H0 and H1, so this would happen first. Then, once we get the data, then we move on to the gather and weigh the evidence phase, so we'll head there next. And then we would start collecting and looking at data. So in that phase we get steps 3 and 4, and step 3 is to compute the test statistic. So since this is a test on a proportion, our test statistic would be a z-score, and that would come from taking the p-hat from our sample, subtracting the claimed p from the null hypothesis, and dividing that by the standard deviation of p-hat. That would normally be the square root of pq over n, but we don't know the true p and q, so we'll use the claim value in there. And that's what we want to plug into, so we just need a couple pieces to be able to do that. We need P0, but that's in HO, 0.3172. We also need P-hat and N. So for P-hat, either that's going to be given in the problem or they're going to tell us the number of successes, so we just need to go track that down. And as I look through here, it says a current sample, so it's a sample proportion, so we're going to look there. It says a current sample of 218. That sounds like that number right there would be N. Had 64 that abused marijuana in the last year, and since that's what we were looking for, that would be our number of successes, X. So it looks like we've got our X over N. Go ahead and plug those into the p-hat formula. So p-hat would be 64 over 218, kind of a small sample for proportion, but that's what we have to work with, so we'll go with that. And then let's see what we've got there. 64 out of 218. Round this to 4 decimal places would be the standard, so that'd be 0.2936. So I would point out right here that it looks like we've got some evidence to support our case. we got a p hat that is to the left of the old value from 2007, and so that indicates some evidence in support of H1. The question is that close enough to 0.3172 that this could actually be true and the difference is just due to random variation, or is that far enough away from the left that we can say no, that's not random variation, or at least it's unlikely that it's random variation, and reject that in favor of H1 being the true claim. So let's go ahead and start plugging in and getting our z-score here. So continuing on with this step, z would be p hat 0.2936 minus the claim value from H0, which is 3172, and then we divide that all by the square root of the claim value, 0.3172, times 1 minus that, so 1 minus this number would be a 6.828, and then divide that by n, our sample size, which we already found when we did p hat to be 218. And then we want to see, is this a small difference or a big difference? So if this measures out to be a small difference, that makes H0 remain plausible and we would not reject it. But if this is a big difference, that's strong evidence that HO is false and we'd reject it in favor of H1. So let's see how it goes. So we're going to want to enter all that into the calculator. Parentheses around the top, so 0.2936 minus 0.3172 divided by the square root of 0.3172 times 0.6828 over 218. And I don't close the parenthesis until I have all three of those numbers, because they're all three inside the square root, and that's the job of those parentheses, is to show us what's inside of the square root. So what I get there seems like a pretty tiny difference, negative 0.749. This is z-score, so I'd put 3 decimal places on it. So this is showing up as a really small difference. We're about a couple percent below the old value, but from a sample that's really small. And with a small sample, it's really small for proportion. And for a small sample, random variation still plays a large role. And so to see a 2% difference is not unusual from a sample of that size. So this remains a plausible value, and I don't think we're going to reject it. But the p-value is supposed to play a role in that as well. I think this isn't a close call, so the p-value is not so crucial. But we'll go ahead and calculate that to see if we had decided to reject it, how big of a risk would that have been. So we go ahead and do the step 4 here. Let's see, right, put that over on this side. So we'll calculate our p-value. So I'll draw the bell-shaped curve. I'll put the claim value in the middle typically, but we're going to show the z-curve right away, so representing the claim value of 0.3172, I'll put the 0. And then representing our p-hat of 0.2936, I'll put its z-score, which would be negative 0.79. And then this is a left-tailed test, and we can see that in H1 because it has a less than. So on a left-tailed test, our p-value would be the area to the left of our test statistics. So I just want to know how big that area right there is, and I can find that using normal CDF because this is z-score, and left boundary negative infinity, right boundary negative 0.749, and we'll go to the calculator and see how big that is. So bringing in the calculator, going to the distribution function, normal CDF from negative infinity, so I'll do the alpha I, just have that big number stored in there, and then negative 0.749 on the right, and we get a p-value of 0.2269. That's our p-value, and that's a pretty big number for a p-value, meaning that if HO was true, there's a decent chance, about 23% chance, that you'd see something as far to the left or farther than that value, like we did with our 2936. And really what we're saying, it could land that far to the left of there just due to random variation. So random variation remains a plausible explanation for why these numbers are different. HO could be true, and that could easily happen, a decent chance of that. So when it comes time to make our decision, and that is the final phase, is decisions and conclusions. I think we're going to come to the conclusion here to not reject H0. And there's two things that I'm thinking about when I say do not reject HO. One of them was my test statistic. The test statistic was negative 0.749, so that's less than one standard deviation apart between these two. And if we think back to Chapter 8, anything that's close to p hat is a reasonable possibility for the true proportion, and their claim value is within one standard deviation of p hat, so that small difference makes this look like a reasonable option. So I'm not going to reject a claim that's claiming something reasonable. And then the other way I could look at it is if I had decided to reject it, this would have been the risk of making a type 1 error, and it's much higher risk than we were willing to accept. We were only willing to go 5%, and this would be over 4 times bigger than that. So I'll also make a mention of that here and say that the reason I did not reject HO is it would have been too risky. And then finally, we are supposed to put the conclusion down as well. And so if we had enough evidence, we would have rejected, but we didn't reject HO, so it must be the case that there is not enough evidence and then we'd state our significance level. So there's not enough evidence at the 5% significance level. And then we'd state what we were trying to show. And in all hypothesis tests, we're trying to gather evidence to show H1, that the true percentage of current 12th graders that abused marijuana during the last year is less than 31.72%. So write that out. So there's not enough evidence at the 5% significance level to show that the true percentage of 12th graders that abused marijuana last year and then what we were trying to show was that that was less than 31.72%. So there was not enough evidence to show that the true percentage of 12th graders that abused marijuana last year was lower than 31.72%. So just some quick comments there. When we say that, we're not saying that we know that it's still 31.72, just like it was back in 2007. We did, after all, get some evidence that it's lower because we got a sample proportion that actually was lower. But that sample proportion was close enough to 31.72 that 31.72 remained a plausible or reasonable possibility for P. So it's not that we got no evidence that it was wrong. We did get some evidence. It was just weak evidence, so we did not feel like it was enough to be confident that HO had decreased. And so we're not going to reject unless we have that confidence. And also you could think of the p-value showing us that there would have been too high of a risk that that was a mistake if we had decided to reject HO with our current evidence. Okay, as we turn the page, we're just going to be continuing on with some follow-up questions to that hypothesis test we just did about the marijuana abuse among 12th graders. So let's move on to Part B. Compute a 90% confidence interval for the true percentage of current 12th graders that abused marijuana in the last year. So they're asking us to do a confidence interval, and it's about the true percentage, which means it's about P. So if I'm doing a confidence interval about P, or proportions, I'm going to use the formula P hat plus or minus Z star times the square root of P hat times Q hat over N. And if we think back to the previous page, we already know our value of P hat. So we had computed that, and P hat was approximately 0.2936. So we're going to use that again, and we know our N was 218. The one piece of this that we don't have is the Z star. There's a temptation on people's part sometimes when they've just done a hypothesis test to grab the z-score off of that hypothesis test and use that here. But remember that when we label this as z star, we're saying we need the z-score that goes with this confidence level of 90%. So we have to make sure that that is tied to the confidence level. So I'll draw a quick picture. And I'm going to do a z-curve where the area in the middle matches up with that confidence level of 90%. That leaves 10% left over. We split that among the two sides, so we'd have 0.05 on each side. And then we want to figure out what z-score goes with that. So that would be z of 0.05. And if we go look on our formula sheet at the t-table, even though it is the t-table, it does have z-scores at the bottom. So if I find the t of 0.05 column, and I drop all the way down to the bottom, that'll give me the z-score of 0.05, which is 1.645. So I'm going to put that down, and that is going to be my z-star. So now we have all the pieces we need. We take our p-hat, 0.2936. That's just from a sample, so we know that's not right. We give ourselves some margin for error, and if we want to be 90% confident, then we have to go out 1.645 standard deviations in each direction. When we're doing confidence intervals, we don't use a claim value because theoretically there wouldn't be a claim value around, so we just use the sample value, and that would be the 0.2936, and then we do q hat times that, which would be 1 minus this number, so that would be 0.7064 if we subtract from 1, and then divided by our sample size of 218. And we just go ahead and separate this off. And then I'm going to copy down the p-hat, and when I'm doing a confidence interval I always want to see my margin of error, so I'm going to show that piece, calculate it separately, so 1.645 times the square root of 0.2936 times 1 minus that, which would be the 7064 number, over 218. And again, just being careful to make sure I take the square root of all of that, so I put the parentheses at the beginning, or the calculator actually does, and I don't close those till I get all three numbers in. When we get our margin of error, we want to match it with our point estimate, so 4 decimal places, so 0.0507. And then to get our interval, we'll want to subtract and add. So 0.2936 was our estimate, but we think we may have been off from the truth by as much as 5%. So we'll subtract that 0.0507, get a lower boundary for 0.2429, and then an upper boundary, when I do the plus case, of 0.3443. And we said at the beginning that what we were doing here was a confidence interval for the true percentage p, so I'm going to just state that again, that p is an element of this interval. Okay, so if you look at that, that really has nothing to do, you would think, with Chapter 9. That's just review of Chapter 8, doing a confidence interval for proportions. But what we're trying to show here, using the confidence interval, sorry, I forgot to write the 3 right there, is how this logic of a confidence interval matches up with the logic of a hypothesis test. If this interval is a list of reasonable possibilities for p, then what we want to notice in that is that our claimed value, which was 0.3172, is falling into that interval, and that means HO is a reasonable possibility for as being a true claim, and we don't want to reject a claim when it seems reasonable that it could be true, and this interval lists it as one of the reasonable possibilities. I mean, I don't see it specifically there, but it is in this range between 2429 and 0.3443. So the next question here actually asks us to write that out. It says, explain how the confidence interval we got right here agrees with the decision we made in the previous page in that hypothesis test. So when they ask me to do that, I always start off with the confidence interval. And if I say if p is an element of that interval, so if p is somewhere between 0.2429 and 0.3443, and I do always say if because we didn't say we were sure it was in there, we said we were 90% confident. But if p is in that interval, that doesn't imply that p is equal to that value from HO, but it could be because that number's in there. So I'm going to say p could be, and then I'm always going to be trying to think about the value from HO, so let me just bring that in real quick. HO said that p was 0.3172, so that's the number I'm going to write here. And again, this interval really says p could be anything in that range, but one of the reasonable possibilities is 3172, and that's special because that's from HO. So if p could be that value, that implies that HO, which stated that p is that value, could be true. And we want to reject claims when we are confident beyond a reasonable doubt that they're false. Right here we're saying it could be true, and really what we mean is it's reasonable that it could be true, and that implies that our conclusion should be do not reject HO. Okay, finally on this example, they have one more question for us. Discuss the possibility that we have made a type 1 or type 2 error in part A. So going back to part A, we said do not reject HO. That was our decision that they're talking about. And they want to know if that was a type 1 error or a type 2 error, or if that's possible. And a lot of times when people see that our decision was to do not reject HO and that the confidence interval matches up with that, they think it must have been a correct decision. But really, both the hypothesis test and the confidence interval were based on a random sample. And that random sample has the potential to not end up having been a representative one, to be biased and take us down the wrong path. And if we get an unlucky sample like that, it's going to lead us to the wrong decision both in the hypothesis test and the confidence interval. So the fact they agree is good for us in terms of the math we did, but it doesn't prove that we made the right decision. It's still possible that we've made an error. And when we think about that, discuss the possibility that we've made a type 1 error or a type 2 error, the first thing I would do is look at my decision, which was do not reject HO. And I would say because we did not reject H0, and then I would say that implies that we did not make a type 1 error. And I can say that with complete confidence because a type 1 error is rejecting HO when it is in fact true. It's impossible to make a type 1 error when your decision was to not reject HO. So a type 1 error is off the table. A type 2 error is possible anytime you decide not to reject HO. Just a reminder, the definition of a type 2 error is not rejecting HO when it was in fact a false claim. And so I didn't reject it because HO looked like it was a reasonable possibility for the truth. That doesn't mean it was the truth. So I would say, however, a type 2 error is possible and has occurred only if HO was in fact false. So a type 2 error is not rejecting a false claim, and I don't know whether HO was a true claim or a false claim, but it's possible that it was either. And so because we didn't reject HO, a type 2 error is possible, and it has only occurred if HO in fact does turn out to be a false claim. All right, that wraps up section 9.2.